Hello everyone, welcome to my own Thesis Defense. Let me start from explaining the key terms in the title. Here, comprehensive means multifunctional and multitask. The AI teaching assistant is a semi-automatic program that assists instructors. And towards means that the UI and other parts of the envisioned system are missing. To illustrate what our AI TA can do, we use the following example. Suppose that one assignment of a comp intro class is to write a Java factorial function, which takes an integer n as the input and outputs a factorial of n. Also, suppose that the instructor's solution code for this assignment is the one shown in the figure. First, let's assume a student came and directly asked about the base case of the factorial function without including any of his thinking or anything he had attempted. This type of question will be categorized as an active question. If an active question is detected, the AITA will reply to the post and request for more thinking from the student. It will also provide the student with specific aspects that the student needs to elaborate more on. After receiving the reply, the student added his question and provided his reasoning and attempt to the question, which changes the post to a constructive question. Once the AITA detected that the post is not constructive, it will forward the problem to the human TA through an email, since constructive questions are related to assignment implementation and the human TA should be responsible to answer them. After receiving the notification, the human TA can and provide the answer to the question. After the first base case question, a new student came and asked a duplicate question to the previous one. The AITA will then identify the duplicate post and reply with a link to the previous post, so that the student can get what he needs without waiting for the instructor to answer the question again. Moreover, the AITA can detect incompleteness in Piazza office hour requests. If the request does not specify a time to meet with the instructor, the AITA will detect it and ask a specific meeting time from the student, so that the instructor does not need to spend the whole office hour session to wait for the student. If the request does not give a detailed description about the problem, the AITA will ask the student to further specify the problem by illustrating more on the concept it's provided, so that the instructor can prepare for the problem in advance. If the request specifies neither the meeting time nor the reason, the AITA will ask the student to give both parts of the information. If students have difficulties about the assignment and want to know the complete implementation of the code, the AITA will detect the specific function that the student asks and reply with a line-by-line English translation of the solution code, so that the student can have a detailed idea about how to implement the function without violating the course policy. For all functions mentioned above, the AITA will send its proposed reply to the instructor and ask for confirmation before it posts the response. If confirmed by the instructor, the AITA will directly post its reply on Piazza. Otherwise, the instructor can edit the reply before it gets posted, or the instructor can cancel the reply. The instructor can also choose to trust the AITA and make some functionalities fully automated without granting confirmation from the instructor. Not only is the AITA able to help students with learning, it can also help instructors with teaching with its instructors-only features. For example, suppose there are many content clarification questions about this assignment, which indicates that many students cannot understand certain instructions of the assignment or some aspects of the assignment is unclear. Then the AITA will post a note to the professor of the course, since this is a content clarification question, and the professor should be responsible to answer it. In the note, the AITA will ask the professor to provide more clarification about the assignment by specifying the major concerns from the students. Meanwhile, the AITA will send the content of the note to the professor through an email. At any point during the semester, the instructor can ask the AITA to generate a report for each student in the class. The report includes three parts. The first one is the number and type of posts that each student has since the beginning of the class. The reason why this is included in the report and why the type in the table are active, constructive, content clarification, and logistical is because according to the finding of the group of researchers shown on the top right corner, there is a significant correlation between the number and type of questions that a student asks and his final grade of the course. As a result, by using the same type mentioned in that paper, the AITA can predict students' final grades based on their results. The course draw probability of each student can thus be predicted based on their final grade prediction. The 6 functionalities are so far the ones proposed by us. In the future, more functionalities will be added to make the AITA more capable and comprehensive. According to our plan, the AITA will be divided into 4 compartments, which is the database, the kernel, the connection module, and the user interface. The thesis will introduce all 4 compartments, but the main focus will be on the implementation of the kernel. Currently, the kernel is divided into 4 modules. The first module is called the automatic labeling system, which labels the new posts into the 4 pre-designed categories mentioned above. The second module is the duplicate post identifier, which is used to identify duplicate posts. The third is the incomplete office hours request identifier, which is used to identify office hour requests that do not specify the time or reason components. The last is automatic assignment assistant, which is designed to help students with questions related to code implementation. For the 6 functionalities mentioned above, the automatic labeling system will serve as a basis for 3 of them, since all these functionalities requires identification of posts of certain categories. The duplicate post identifier is used for duplicate post identification. The incomplete office hours request identifier is used for incomplete office hours request identification. And the automatic assignment assistant is used for code assignment assist. The pipeline we use to build each module is similar. We firstly collect the data needed for the module, then we clean the data using different strategies. After that, we extracted features from the data, which was used as the learning material of our model. Next, we set up our prediction model. Finally, we train the model using the features extracted and test it using the test data. Now, let me introduce the implementation and the results of the automatic labeling system. The data we have for this model is 7,279 piazza posts from 13 different courses of the Computer Science Department of UNC Chapel Hill. There are 3 different course groups in our dataset. One is Foundations of Programming, another is Computer Organization, the third is Modern Web Programming. These 3 course groups will be referred to as Comp 401, Comp 411, and Comp 426 in the following slides. After obtaining the data, we manually label the posts into one of the 4 categories: active, constructive, logistical, and content clarification. The definition of the 4 categories can be visualized as the following tree structure. First, if the post is a logistical question, then it will be labeled as logistical. Otherwise, we determine if the post contains information about a student's own work. If it is irrelevant to the student's work, then it is labeled as content clarification. Otherwise, we determine if the post shows students' reasoning or attempt to construct a solution to the problem. If so, then it is a constructive post. Otherwise, it is an active post. Here, we show one representative example for each category that was labeled by the automatic labeling system. According to the image on the left, the active question directly asks for help without showing any knowledge about the concept or any attempt to solve the problem. On the contrary, when it comes to the constructive question, the student clearly shows his attempt to solve the problem. The logistical question is asking about the LA office hours, and the content clarification question is asking for clarification about a project, which is irrelevant of the student's own work. After labeling the posts, we clean the post context using the following 6 methods. The first one is clean, which removes special characters such as markup tags that help display certain styles of characters or formulas. For example, in the example shown here, the special characters in the red box is removed. The second one is hyperclean, which is used to unify and correct spelling of the same meaning words. For example, in this example, the word improvement is spelled incorrectly and is corrected after running the algorithm. Also, the abbreviation CS is changed to computer science to keep unification. The third one is remove punctuation, which removes all punctuations that appears in the content. For example, the question marks in the red box are removed. The fourth one is remove stop words, which removes all stop words that appear in the content. Here, the range of the stop words is defined by the stop word set in nltk.corpus. In this example, you can see that it removes most words of a sentence and only 4 words left after the cleaning. All the words in the red box are eliminated. Since this stop word set is large and it may overclean the content, we made another stop word set with much less but very common stop words. In the new example, the original sentence is the same, but the cleaning result retains more information compared to the previous example, and fewer words are eliminated using the reduced stop word set. The last one is stem words, which shortens the words to their stem forms. For example, in this example, all verbs tense are removed. Also, all the comparisons of the adjectives are removed, and the nouns are unified to their singular forms. Of all 6 methods, the clean method is a default method, which is always used when cleaning the posts, and all other methods can be switched on or off. It is common sense that the more cleaning methods we use, the more concise that the content will be, but that also leads to greater information loss. According to our experiments, the best result appeared when we did hyperclean, we removed punctuation and stop words using the reduced stop word set, but did not shorten the words to their stem forms. Now we have our clean post, but if we directly put this into the prediction model, it will not work. This is because most existing machine learning methods cannot directly process text data. As a result, it is necessary to find an appropriate method to transform text data into numerical data. To apply machine learning to natural language processing, language models are introduced. The key idea of language models is to map the context into numerical vectors of certain dimension, namely an array that contains a certain number of elements. For example, the output vector of the word hello can be a vector like this one, where the value of each element indicates the significance of the semantic meaning of the word in one direction. Although the actual semantic meaning that each array element stands for is unknown to human, it is interpretable and learnable from a machine's perspective. Each array has n elements, or dimensions, which is different for different language models. The more dimensions that a vector has, the higher resolution it has with respect to semantic meanings, and will make the machine learning model understand it better. After getting the numerical vector of each word, we sum them up and get the numerical vector of the whole post. This is reasonable if we think about the meaning of vector summation. Since each element indicates the significance of the semantic meaning of the word in one direction, the semantic meaning of the whole post in one direction can be represented by the semantic meaning of all words in that direction. In this thesis, we used 6 different language models, whose name, released year, number of parameters that the model contains, and the length of the numerical vector are shown in the table below. The number of parameters is another indicator of the model capability, where more parameters indicates more complicated and more capable model. Also note that there are multiple submodels for each of these models, and we used and show the most capable submodel of each language model. One language model that's worth noticing is GPT-3, who has at least 100 times more parameters in its neural network and 8 times the vector length of the other language models. This is also the most capable language model so far. In this thesis, we put the clean post into 6 language models respectively, each of which outputs a numerical vector, which represents the semantic meaning of the post. We then put each numerical vector into our prediction model as the learning material and get the prediction results. In this thesis, we set up 4 prediction models using the random forest classifier, XGBoost, which is another classifier popularly used in recent years, convolutional neural network, and long short-term memory, which is a refined version of the recurrent neural network. Each prediction model predicts and outputs its result independently. Therefore, for the first module, we label the posts into 4 categories. Then we clean them using 6 different strategies. After that, we put the clean posts into 6 different language models to create different numerical vectors. Finally, we set up 4 different prediction models and obtain prediction results from each model after they learn from the numerical vectors for the posts. Now let's see how the models perform. This is the accuracy plot of each of the prediction model paired with each language model. Here, the training data is 80% of all posts, while the test data is the rest 20% of all posts. According to the figure, there is a clear improvement in accuracy from Virtual-VAC to GPT-3. On the contrary, the performance difference between different prediction models is less obvious. The CNN model gets the highest accuracy for most language models. From our perspective, this is due to the complexity of the model. Since we use 6 convolutional layers with different filter and kernel sizes when setting up our CNN model, it has a stronger capability to identify features that are neglected by other models. On the other hand, XGBoost performance is relatively worse compared to other models. This is because the parameters of XGBoost models usually need to be fine-tuned in advance to ensure better performance, while we kept most of the parameters in their default settings when setting up the model. To see how each language model performs in other prediction tasks, such as using one group of comp courses to predict another group of comp courses, we plot the heat map of the prediction of each language model paired with the CNN prediction model since it has the best performance. I will illustrate the rules about how we select the training and test dataset with this simple heat map. In the actual heat map, the title will be replaced by one of the language models. The labels on the X and Y axes are defined the same as before. The labels on the Y-axis is a training dataset we used, and the label on the X-axis is a test dataset. There are 3 different cases when choosing the training and test dataset. First, for all leading diagonal cells, the training and the test dataset are using the same course group. So we split the post and use 80% of them as training data, and the rest 20% as the test data. For example, in the scenario in the orange circle, the training data is 80% of the Comp401 posts, and the test data is the rest 20% of the Comp401 posts. Case 2 describes a situation when the training and test data are using different course groups. So we directly use the course group specified as a corresponding set with no data splitting. For example, for the scenario in the green circle, the training data is of the Comp401 posts, and the test data is of the Comp411 posts. The third case happens when either the training or the test data use all course groups. In this scenario, for the set that does not use all course groups, we directly use the group specified as a corresponding set with no data splitting. For the set that use all course groups, we use all the posts except those in the group of the other set with no data splitting. This will ensure that there is no overlap between the training and test set. For example, for the scenario in the blue circle, the training data is of the Comp401 posts, and the test data is of the Comp411 and Comp426 posts. On the other hand, in the bottom left corner, the training data is of the Comp411 and Comp426 posts, and the test data is of the Comp401 posts. This is the actual result of all language models. Similar to the line chart shown before, there is a pattern of performance improvement from Virtual-VAC to GPT-3. We also found that the cells in the leading diagonal have higher accuracy than other cells. This is reasonable since the same courses taught in different semesters are usually closer in style than other courses. As a result, students tend to ask similar questions. On the contrary, since different course groups are different in teaching styles, and the questions that students ask in different courses are very different, training on one course group and predicting on another course group is not ideal. However, we also found that the difference between the diagonal cells and other cells gets smaller from Virtual-VAC to GPT-3. This is because as the language model use becomes more capable and the dimension of the numerical vector gets larger, the model can understand the semantic meaning of the posts better. As a result, the style and category ratio difference between different courses can make less impact on the models, since the definition of each label, which all models try to learn, stays the same for all courses. For the other modules, we used similar pipelines to build each of them. The implementation details are omitted, and a summary of the results of these modules is the following. In the duplicate post identifier module, we managed to achieve the highest accuracy of over 98% using the GPT-3 model. We also found that the trained model had a strong capability to identify duplicate Piazza posts in different semesters and posts that are complicated. In the incomplete office hour request module, we managed to achieve 100% accuracy for all model combination when identifying the time component, and the highest accuracy of over 95% using the GPT-3 model for the reason component. We also found that the model was capable to identify the deficiency in students' requests and generate satisfying automatic replies. In the automatic assignment assistant module, despite the unsatisfying translation of the solution code, we successfully showed that the model is capable of identifying students' questions about specific code implementations. For future work, it is possible to further improve the accuracy of the models. This can be split into three parts. First, all language models introduced in this thesis are pre-trained for general-purpose natural language processing. However, our tasks are computer science specific and involve many terms about the subject, which prevents the models from achieving higher accuracy. To solve this problem, all language models should be fine-tuned for our task. Second, when setting up the prediction models, we left most parameters of our models to be the default values, which hinders the models to achieve better performance since optimal parameters should be different for each task. In the future, it is necessary to fine-tune the prediction models by adjusting the parameters. Third, while one model may mistakenly assign an incorrect label to a post or request, combining the decision of multiple models can avoid this problem. For each task, it is better to train multiple prediction models independently and combine them. Also, the AITA needs to be completed by implementing other compartments. To make the system fully functional, a database needs to be set to store student posts and office hours requests. A connection module needs to be built to serve as a communication medium between the forum and the kernel. And the user interface needs to be added to allow the instructors to change settings of the system and add or disable functionalities of the kernel more easily. Besides, in this thesis, the modules we have already built can only realize 3 of the 6 proposed functionalities, and the rest requires either extending or refining an existing model. Moreover, it is always possible to add more models to realize more functionalities. Finally, it is possible to make the automatic assignment assistant work by using a more capable code translation model. Currently, the model we are using is a GPT-3 model developed by OpenAI. Despite its great performance in all other sections of the thesis, it was not trained specifically for code translation. Now, OpenAI is developing its new model called Code-X, which is specifically trained for code translation. While this model has not been open to public, it has shown great code translation performance in private tests. Once Code-X becomes available, we can use it to refine the automatic assignment assistant. The work in this thesis is done by 3 members. Hao Wang, the second author of the thesis, labeled the posts used for training the automatic labeling system and tested the code for the duplicate post identifier. Kaizhuo Chen, the third author of the thesis, labeled the posts used for training the automatic labeling system and the office hour requests used for training the incomplete office hours request identifier. We would like to thank Dr. Duan, the advisor of this program, for offering precious guidance and resources. We also gratefully thank Dr. Majaikis, the second reader, for reviewing the thesis. This is the end of my honor thesis presentation. Thank you for watching. Any questions?